Hi, I'm Mark. I'll tell you today about our paper, The Price of Incentivizing Exploration, a characterization via Thompson sampling and sample complexity. And this is joint work with Slivkins. Our motivation comes from recommender systems. We use these every day. You can be recommended a movie to watch, a restaurant to dine in, a vacation destination, a product to buy, a route to drive, and even a doctor to see. The ability to make good recommendations is a large part of the value proposition for many of these businesses, and more broadly, a large part of the modern internet economy. Let me walk through the typical situation for a recommendation system. First, a user arrives and needs to choose a product among some set of alternatives. The system gives a recommendation, possibly with some extra information such as ratings, and then the user chooses a product and ideally leaves feedback. Crucially, the recommendation relies on feedback from previous users, and the feedback can be used to improve future recommendations. So each user plays a dual role, both as a consumer and a producer of information. In the interest of the common good, some users should explore, i.e., try various unexplored alternatives to gather information. Other users should exploit to harvest the fruits of other exploration. So we'd like the recommendation system to manage this balancing act for us and make everyone happy. This is sort of the utopia we'd like to live in. However, there is a problem, which is that agents can ignore our recommendations. If a new action is untested but has some potential, we'd like to explore it for the common good, but no individual agent wants to try it first. There are some potential ways around this. We could offer financial incentives or points for exploration. But in addition to being prone to selection bias, these may not always be feasible. For instance, if we are running a medical trial. Instead, we will consider a different approach. We will create information asymmetry by selectively revealing information to the agents. Let me now explain the model. There are K actions and T rounds. In each round, a new agent arrives, and an algorithm recommends an action. The agent chooses an action and reports his or her reward. For simplicity, we will take rewards to be either 0 or 1. All of our results can easily be extended to the case in which rewards are in between 0 and 1. We assume rewards are IID, which means that each arm's reward is Bernoulli with some unknown reward probability μi. In particular, nobody knows which arm is the best, but we assume that there is an independent Bayesian prior across the arms, which is common knowledge to everyone. The objective for the planner is social welfare, which just means that we'd like to maximize the cumulative reward. If all agents follow the recommendations we give them, this is simply a multi-arm bandit problem, which is a classical problem in machine learning for studying exploration versus exploitation. Since agents do not need to follow recommendations, we will restrict to the algorithms which are Bayesian incentive compatible, which means that they want to follow our recommendations. More precisely, given that we recommend action A at time t, the expected reward of action A must be at least as large as the expected reward of any other action. To be clear, our algorithm is public information, but the feedback it accumulates over time is not. Let me point out that by the revelation principle, we may assume that our messages to agents are just recommendations, and it's useless to add other information like ratings or reviews. This model was introduced by Kremer, Mansour, and Perry, and has led to quite a lot of work. Broadly, incentivized exploration is at the intersection of 3 areas. The first is multi-arm bandits, which is the problem without incentives. The second is Bayesian persuasion, which is, roughly speaking, a single round of our game. The third is social learning, which studies the dynamics of learning and interacting agents. However, note that here we are kind of organizing the learning and interaction of the agents. So it's not total anarchy. Okay, so returning to the story, our main question is how much performance loss is caused by the incentives. The most natural yardstick for this is the regret, which is the usual performance measure for a bandit algorithm. This is simply the suboptimality cumulative over time compared to just choosing the best action, which again, we do not know at the start and need to learn. A second yardstick we will use is sample complexity, which we denote by T sub SC. This is the time needed to almost surely sample each arm once. Without incentives, this is simply K, the number of arms, because we just sample one arm at a time. However, with incentives, it may become difficult to sample arms which have a low prior mean. And we'd like to study how difficult it is to get to these arms at all. The main previous results for this problem are due to Mensur, Slivkins, and Sellke. They show how to match the classical square root T regret for ordinary bandits up to a multiplicative constant factor. However, this constant factor depends on the priors, and the upper bounds they obtain may be exponential in many parameters, such as the number of arms. And they give no lower bounds and no real way of obtaining sub-exponential upper bounds. Our results give a more refined understanding of this price of incentives. In our first main result, we show that Thompson sampling, a state-of-the-art Bayesian bandit algorithm, is incentive compatible as long as it has been given enough samples of each arm. This reduces the price of incentives to sample complexity because the Bayesian regret is at most the amount of time needed to collect these samples plus a square T bound given by a very good bandit algorithm. This number of samples is rather mild, and in fact, not needed at all if all prior means of the arms are the same. Previously, even in the case when the arm priors were IID, it was not known how to obtain something better than a multiplicative blowup in the regret. Second, we give upper and lower bounds for the sample complexity, which match on any problem up to polynomial dependence, in the sense that the upper bound is polynomial in the lower bound, as well as the inverse standard deviation of the most concentrated arm. This allows us to resolve polynomial versus exponential dependence of essentially any parameter in a variety of examples. For instance, we can specialize these general results to some cases and derive corollaries. When all arms lie in a fixed collection of types, we show that the dependence for sample complexity on the number of arms is either linear or exponential, a sharp dichotomy. When all the priors have full support, the dependence is always linear. We also investigate the dependence of the sample complexity on the concentration of the arms and show that it is, roughly speaking, exponential in a variety of special cases, including the case of beta priors. Let me now turn to how we obtain some of our results, beginning with Thompson sampling. As sort of warm-up, I will show you why Thompson sampling is incentive compatible when all the prior means are equal. Let me recall that Thompson sampling is a very natural Bayesian bandit algorithm defined here, in which the probability to sample an arm at a given time is just equal to the current posterior probability that this arm is the best arm. So if some arm has a 10% chance of being the best, according to everything we know now, we will sample it with a 10% probability. So to show that any algorithm is incentive compatible, we need to show that this conditional expectation of mu I minus mu j, given that we recommend arm I at time t, is non-negative. We can rewrite this first by just applying a weighted version of Bayes' rule to compute a conditional expectation, and then by applying the definition of Thompson sampling to replace instances of a probability that we recommend arm I with instead a probability that arm I is optimal. The key insight here is that the numerator consists of a product of two terms, which are each martingales because they are conditional expectations or probabilities at time t of some event, which is now independent of time. Moreover, these martingales are both associated with arm I being good, and in fact can be showed to always move the same direction given any feedback. This means that their product is a submartingale, which means that it can only increase on average. This means that the numerator, which has an outer expectation, is always non-negative because it starts at 0. This is exactly the condition that the prior means are equal. As a result, we conclude that Thompson sampling is incentive compatible when the arms have the same prior means. Showing that Thompson sampling is incentive compatible after initial samples goes by analyzing the same kind of expression. Now we take an additional step of replacing this blue conditional probability by the underlying event. This is possible because we're multiplying two conditional expectations at time t. And so the outer expectation of this product is always the same as replacing one of them by the underlying event. If we also remove the red conditional expectation, then we get something that's manifestly positive because it's just a product of mu I minus mu j times the indicator that mu I is the largest. We can get an explicit lower bound for this using the FKG inequality, which is a correlation inequality from statistical physics. And now we just need to show that we obtained a small approximation error. To show this approximation error is small, we use a Bayesian version of the Chernoff bound to show that the posterior distribution of mu I concentrates around its true value given enough samples. Now that we know Thompson sampling is incentive compatible after receiving enough samples, let me tell you how to collect these samples. Our goal here is simply to obtain one sample of each arm with an incentive compatible algorithm. And for simplicity, we will assume that after observing any arm once, we know its value of mu I exactly. In reality, we have to obtain many samples just by repeating and get a good approximation. We're going to explore an order of the prior means, starting from the best arm. To explore arm j, we will first get started by sampling it if all the previous j-1 arms were terrible so that it actually looks like the best arm. This event may have exponentially small probability, but we will now grow this probability of having explored arm j at an exponential rate. To do this, we use a loop with 3 branches, which are called j-exploit, explore, and exploit. J-exploit is the main one, in which we leverage any previous exploration of arm j into exploitation. If we've explored it with probability pt, then roughly speaking, we can leverage it for lambda pt exploitation value, where lambda is a constant that we hope to maximize. By doing this, we counterbalance a probability lambda pt of fresh exploration. The result is an exponential growth rate of the exploration probability. Finally, if we do neither of these, we just exploit, which allows us to essentially skip the turn. The result of doing this is an exponential growth of the sampling probability, and the rate depends on this constant lambda. It turns out that lambda has a clean definition as the minimal expected advantage of any arm j over any weighted average of the previous arms. This comes from a connection to a 2-player zero-sum game and an application of the minimax theorem. Moreover, although I won't get into the details, we give a polynomial optimality result, which almost always turns out to mean that the sample complexity is polynomial in lambda, where the exact exponent is between 2 constants. As a result, to understand almost any example, we just need to estimate this rather explicit value lambda defined here. Perhaps the most natural example is beta priors. What we show here is that if all arms have standard deviation at least 1 over m, then the sample complexity is at most k, the number of arms, times m to the O of m. So roughly speaking, it's linear in the number of arms and exponential in the strength of the prior beliefs. this is tight when multiple arms have a small variance. But if only one arm has a very small variance, we can actually obtain a better estimate, which is polynomial in the smallest variance and exponential only in the second smallest variance. Both of these results are proved simply by estimating lambda using the general results in the previous slide. The takeaway here is that, at least in the case of beta priors, incentivized exploration is exponentially hard if and only if multiple arms are concentrated. Finally, there's a caveat which I've been sweeping under the rug, which is that not all arms can be explored at all. There's a characterization which, up to edge cases, is quite simple to state. If an arm's prior mean is better than the worst possible performance of all other arms, then you can explore it, because it's always possible to get off the ground when all other arms look bad. But if your prior mean is always worse than some other arm, then a simple induction shows that you can never be explored. So actually, our algorithms explore the set of all explorable arms. But there are some kind of natural limitations to what can be achieved. Let me conclude by giving some list of open directions. All of our results today were for the case of independent priors. This is because of some technical limitations, most notably this FKG correlation inequality, which is used in many places and requires things to be independent. And it would be very interesting to extend these results to correlated priors. There are also many richer problem settings to study, such as long-lived agents who visit repeatedly and situations where some observations are inevitable of the past history. Finally, it's an interesting direction to study if, by looking at many different types of agents, we can use diversity to help incentive-compatible exploration. Thank you.